Geothermal webinar series. This is a collaboration between Think Energy and Enerchange. And once again, I am Carlo Cariaga of Think Energy. And today we have the pleasure of hosting Veronica Schwarz from Orcan Energy to talk about modular ORC solutions for flexible geothermal power generation. Now, I've always been a fan or an advocate of modular power generation solutions. I think it's a very useful mechanism for reducing risk, especially in early stage geothermal development. But I will let Veronica talk about it more. So Veronica holds a master's degree in mechanical engineering from the Technical University of Munich. It has been with Orcan Energy since 2018. She has gained broad experience in both technical and commercial roles in her time in the company. In her current position as a sales engineer, she is responsible for key accounts in the European industrial and geothermal sector. She works closely with project developers and operators to support power generation from geothermal heat using modular and flexible ORC solutions. To everyone in the audience, please feel free to write in your questions. There should be a questions tab somewhere in the webinar panel, so you can just type it in anytime and we'll get to those questions after Veronica's presentation. And with that, Veronica, please take over.
Well, thank you very much, Carlo, for the kind introduction. Hello, everybody. I'm very happy to be here today and to talk to you about flexible power generation from geothermal energy. But before I'm gonna dive right into the topic and gonna tell you a little bit what I even mean by flexible power generation, let me first very quickly just introduce the company I work for, Orcan Energy, and tell you a little bit about what we do for those of you who don't know us yet. So Orcan Energy is an ORC producer from Germany, and we produce modular and standardized ORC solutions. So here in the first picture, you can already see some of our modules in one of our installations. We were founded in 2008 here in Munich in Germany, where I am also located. And since then, we have gained quite a bit of experience. So we're not just in the geothermal sector, but we have applications basically everywhere where you have heat that can still be utilized for electricity production. So there's applications all over the world in especially also in industrial applications like cement, steel production, oil and gas also. We're also in the power sector, such as engine power plants, where we use the heat from the exhaust gases and from the jacket cooling water of the engine to produce additional electricity and improve energy efficiency. And one, I think, very interesting application, completely different than all the other ones, is in the marine sector. So there we also utilize the heat from the ship's engine, exhaust gas, and the cooling water, and we produce electricity right on board of the ships. So there's all kinds of different applications, but of course today we're gonna talk about the geothermal sector. Just wanted to show you so far we have over 600 of our standardized ORC solutions worldwide, with over 7 million operating hours and counting. And the key technology behind all of these applications is the ORC technology. So ORC stands for Organic Rankine Cycle. Now, I'm sure a lot of you have heard about Organic Rankine Cycle before, but just for those who haven't, I'm gonna explain it very, very quickly, just very briefly. I'm not gonna go into any technical details, but generally, I think you have all heard of regular steam power plants before. Let's say, for example, in a coal power plant, what happens is that you burn the coal and the coal heats up water. That water evaporates, so you have steam. And that steam then goes to some kind of expansion machine. So usually it's a turbine. By expanding the steam, it drives the turbine, and that's connected to a generator. So that's how electricity is produced. And then after that, you want to bring the steam back to its initial state again. So you have to condense it. That means you cool it down so it's liquid again. And you have a pump to raise the pressure. And then it's closed loop. It's at its initial state again. And you can start electricity production all over. ORC works in exactly the same way. So that's also why what I just described is exactly what you can see here in this picture of the ORC cycle. But the main difference is that instead of water in this closed loop system, we use an organic refrigerant. So that's also why it's called organic Rankine cycle. And the great thing about these organic refrigerants is that they have a much, much lower boiling point than water and also need much lower pressures for electricity production. So that means that we can use heat sources at much lower temperatures than you would with a steam power plant. And also we can build the systems a lot smaller, a lot more compact, a lot simpler. They're a lot simpler to operate and maintain than those big steam power plants. Now, ORC technology itself is nothing new. It's been around for many decades. There is many companies producing ORCs, but what we do a little bit differently, what I already mentioned in the beginning, is we modularized and standardized the ORC system. So here you can see the two machines that I think should be the most interesting for the geothermal sector. And we always build the same machines. So it's the same machines for all applications. Doesn't matter if it's in the oil and gas sector, in the cement sector, or the geothermal sector. We can use the same machines for all of these applications. We always use the same parts, and then just depending on how much heat there is, we can scale up or down. So we just use multiple machines. We can use 1, 2, 5, 10 machines in one place to make the power plant the right size, but we don't have to design a new customized power plant every time. So usually the process is that you design really for every application, you make a new design for the power plant. Instead, what we have are these standardized machines where we just use the same machines in all applications. So that's really nice for us because we don't have to do a lot of design work all the time and put in all this engineering efforts for every application, but we can just produce the same machines. But how does this actually help you? Well, the whole idea behind the modular and standardized options is that we really saw that there is so much heat potential that is currently not used by those big power plants. And the reason was usually because it's either too much, too hard, too difficult, too complicated to implement, to operate. So it's a lot of effort, or the risk is very high. We all know, especially in geothermal, there's already a lot of risk involved with the wells, how much energy you're actually going to find. So adding more risk that the power plant design is not going to be right is, of course, not very helpful. And then also, of course, it has to be economically viable. So those are the three things that we really wanted to tackle with our machines, is minimizing the effort that you have both for implementing and operating, minimizing the risk involved in your investment, and then maximizing the value. So maximizing the economical value, but also maximizing the value that you get from your geothermal heat. I think geothermal power is such a valuable resource, and we should really make sure that we use as much of it as possible and that nothing gets wasted. So I already mentioned those are the two machines that I think are interesting for the geothermal sector. I don't want to go into big details about the products themselves. I want to talk more about the general idea of a modular power plant but just that you know the difference. So on top, the smaller modules, they are for smaller amounts of heat. So one can produce up to about 200 kilowatts of electrical power. So for smaller heat sources, and also for lower temperatures starting at 80 degrees. And then on the bottom, those are our new bigger modules. So they are really for larger scale heat sources starting at 8 megawatt thermal, and also for a little bit higher temperatures. So here the operating ranges start at about 120 degrees. So just for different applications, but same principle, that depending on how much heat you have, we would just put multiple modules of those at one side, or they could also be combined, but that's going into a lot of detail. So let's talk a little bit more about the general modular design. So how do we actually minimize the effort that you have on site? Well, for the installation, it's really important that the systems are designed as plug and play systems. So that really means they are mounted in our factory, and then they come to the site. They just have to be connected to the heat source, and they are ready for operation. So they're already assembled in the factory, they're tested in the factory, and that also ensures very, very high quality, and therefore they are very reliable. Because of course, if you assemble something in a very controlled factory environment, it's a lot easier to ensure the highest quality standards than doing that on the site where you have a lot of outside factors that can make it a little bit harder to maintain this high quality standard. So the more we can really assemble and test in the factory, the better. And also the quicker the installation then is, and the less work on site. And after implementation, once the machines operate, the maintenance is also very, very minimal. So we only have maintenance once a year, between 1 and 3 days per machine. And it's just very minimal maintenance that has to be done, because we only use standard off-the-shelf components. So all of the components inside our machines are not specialized components designed by us, manufactured by us, no complicated turbine design. Instead, we use components from very big, very well-known producers that produce those components in big numbers in factories all over the world for all kinds of different applications. So that means the availability of those components worldwide is very high, and also means they are very, very reliable, because of course I already showed you we have 600 of our modules worldwide. So we already have quite a track record in how those components have to be operated, how they have to be maintained. But the manufacturers of these components, they produce very, very high numbers of those. So they have even more experience in how they should actually be operated and maintained. So that's how we can really keep the maintenance to an absolute minimum and assure very high reliability of the modules. So now that's the part about minimizing the effort. What I think is even more interesting is to minimize the risk and to maximize the value, because that's where the flexibility of those modular solution comes in. So for one, we can adapt through a scalable design to changing heat loads, and we can also be very easily combined with multiple heat users. And those two things are actually something I want to explain a little bit further for the geothermal cases. So the great thing about geothermal heat is that it is completely stable. It's compared to wind or solar, it's the big pro of geothermal power is that its base load renewable energy that we have available. So it's amazing. We have a very stable heat supply. But now, if we actually use the heat as heat, let's say in a district heating network, for greenhouses, for industrial applications, the demand is not going to be stable. So it's going to be a little bit different depending on the application and where you live, but usually it's very seasonal. So this is just an example of a district heating in Germany. So you have very big fluctuations over the course of a year. So what that means, if you just use the geothermal source for heat supply, there's going to be a lot of heat that is unused. And I think we all know geothermal wells are pretty expensive. There's a lot of risk involved. So we really should make sure that we use as much heat as we can of this valuable resource. So the solution could be to add electricity production. That's a great idea. But as you can see, the differences in electricity production are in available heat here are pretty high. So there are times in the year where there's very, very little heat available, and then there's times in the year where there's almost all heat from the geothermal source available. So it's going to be really hard to design a power plant that can handle those very big fluctuations. And that's where the modular system comes in. So just from a design point, any geothermal power plant is going to have some restrictions for part load capabilities. And for our units, for example, we can, depending a little bit on the conditions, we can go down about 50 to even 30% part load for one machine, which is already pretty good. But if you have these high fluctuations, that's not going to be enough to handle all of those fluctuations. So that's why it is so great if you don't just have one power plant that can go down to 50 or 30% part load, but you have multiple machines and each of them can go down to 50 or 30%. And they can turn off one by one, they can turn on one by one, just depending on how much heat there is. So what that would look like is that you might install a first ORC module, and then you can see, okay, this ORC module would really run almost all year and produce electricity. There's only in the very, very peak times it would not be in operation, but there's also still a lot of heat that is unused. So then you can install a second ORC unit, still has very high run times and uses a lot more of that heat. So you can install a third one. Their run times are already getting a little bit lower, but still quite a bit. And you can even install a fourth ORC unit, and then basically all of the heat is used. So just a teeny tiny bit is left over, but almost all of the heat is used. But of course, this last unit only runs about half of the year. So the runtime isn't that high. So this would really be an economical question if it makes sense to have 4 modules or if it would make more sense just to have 3 modules. But this is also something you can play around with and you can optimize a little bit to fit exactly to your application what is best for you. So it just gives you a lot of flexibility in terms of how you want to size your plant, and you can also adjust that later on. Also, one thing I just quickly wanted to mention, I'm personally not the expert on that because I'm not a geothermal expert. I'm more in the ORC business, but what I have heard a lot from our customers that it is very, very important to have stable operation for the geothermal pumps, and that this can really, really, especially this flexible design where we can make sure to really always use the heat, that you have very stable operation. This can be very helpful to prolong the life of the pumps, and can be very important for your operations. So that could be another perk aside just from the electricity production. Now, this example is for heat changes that occur over the course of a year. But of course, what can also happen is that, especially here, what we see a lot is that a geothermal well is drilled, you produce heat, and then they start building a district heating network connected to that geothermal well. And of course, in the beginning, that district heating is going to be very small, so it's not gonna take as much heat, but it's really growing over the years. So heat demand isn't just gonna change seasonally, but it's gonna change over the course of 5, 10, 15 years. And if you size a power plant in the beginning to take all of that heat, then after 10 years, that power plant is only going to work at 50% part load or something like this. So it's not really going to be a great fit anymore. So what you can also do, if you don't have that much heat available anymore, you can take machines away. So you can just say, okay, now I just need 2 machines, so we can take 2 machines back. Or if you have additional heat available, you can also add more machines later on. So in any case, you can be very flexible also over time to adjust the size of your power plant, and you don't have to lock in the beginning. So this is the biggest part of taking the risk out of your investment. Even if something changes, you can still adapt, and the units, they keep their value because, like I mentioned, they can't just be utilized for one specific applications, but we use the same machines in all kinds of different applications. And I have one example where we have actually done something like this. So this is a geothermal project in Germany, a deep geothermal well that was drilled and connected to different heat users, so heat and grid greenhouses. And from the beginning, it was very clear that in a couple of years, the other heat users are going to need more heat. So there's not going to be a lot of heat left over for electricity production. But they really wanted to make sure from the beginning, right from the drilling, to use as much heat as possible, as quickly as possible. So we put 6 of our smaller machines there to produce about 640 kilowatts of electrical power, and it was implemented very, very quickly. So this is actually the site. Here you can see how those modules, that's how they come from the factory, so just completely assembled in one shipping container, and they just have to be put there, connected to the heat, and they can start operation. So all of those machines were actually delivered in just one day, and then connected just very shortly afterwards. Usually just takes a couple of weeks until then electricity can be produced. So here electricity could be produced very, very quickly. And then after a few years, heat demand from the other heat users got bigger. So only 3 machines were actually used anymore. So 3 of the machines were sold back to us, and we sold them to different customers in completely different applications. I think one is at a biogas site now. There's also one at a recycling plant, something like this. So completely different applications. But it makes the plant very flexible. And this is also something we offer a lot now in our contracts, that from the beginning we have some sort of buyback option, or can even offer leasing options for the modules to really keep you as flexible as possible and to minimize your investment risk, and also to enable you to really use all of the heat that you have available, so that nothing is wasted. Even in the beginning, all of the heat is used right away. I think another nice example is this geothermal plant in Austria. So also deep geothermal well, and this well is used to heat greenhouses. So they actually grow bananas in a greenhouse in Austria. I think that's really cool. And they had some heat left over. And so we just installed one of our small ORC units to produce about 125 kilowatts of net electrical power. By the way, always when I talk about power, I'm always going to talk about the net electricity that we produce. So that means all of the internal consumers are already deducted, because everything that you need for electricity production is already inside of our modules. So I really want to talk about the electricity that comes out and that you can then really use. So this is the net electricity. And something also to mention, as you can see here, we don't go into machines directly with the clean hot water, and that is really why we can standardize these machines, because we standardize this interface, so it's always hot water, clean hot water, and that's why these machines can be used in so many different applications. And it's the same machine for geothermal or for cement applications, because we standardize the interface for the heat sources. So I think this is a great example for a smaller geothermal power plant, that it even makes sense, even in really small scale, so just 125 kilowatts, it makes sense to use the heat if you have it available to produce electricity. And especially for decentralized electricity production, something I've been seeing more and more, for example, in the oil and gas sector, that there is smaller wells, maybe smaller test wells, and they're scattered over a very big area. So it would be really difficult to actually use the heat that is produced there, because you have to bring heat from a lot of sources, a lot of piping to one central location to build a big power plant. And instead, it's a lot easier to have smaller machines like this as wellhead generators to be installed right there at the smaller well to produce electricity right there and then, because it's a lot easier to lay some electricity cables than to put geothermal piping over very big areas. So that can be a great application for those decentralized applications. One other example I wanted to mention is a project that is currently in installation. So this is a geothermal project we're doing in Taiwan. We're doing this in 2 phases. So first 6 units will be installed to produce about 1 megawatt, and then later on 6 more modules will be installed to produce another megawatt of net electrical power here. Here again, the same thing. So we have the geothermal well, we have a heat exchanger in between, and then clean water loop connected to those machines to produce the electricity. I think here the interesting thing is, so here we don't have any other heat users. Here it's really just about the electricity production. And here the modular approach can really help to de-risk the investment, because there is lots of risk already involved in the drilling, how much heat you will actually find, and the modules don't lose their value, and they can also be adjusted, the number of modules, depending on how much heat you find. And another big perk is that they can be installed very quickly, and it's also easy to implement and operate and maintain in very remote areas. So I think I haven't actually mentioned the operation yet. I just talked about the maintenance, but operation, it's completely autonomous, so no personnel needed at the site. they automatically just turn on when there's heat. They turn off if there's no heat. They adjust automatically if there's fluctuations in the heat. So there's really nothing you have to do. They can be always monitored remotely, of course, but you don't need anybody at the site to operate the machine. So it's perfect for those remote areas and decentralized applications. So far I have been talking a lot about the smaller machines, but if you paid attention in the beginning, I also showed you a picture of these machines. So this is our newest development because we saw a lot of demand also for bigger scale applications and also flexibility for those bigger applications. So we developed some bigger modules. The principle is still the same, but the scale is bigger now. So they are still scalable, where we can still put multiple modules in one site to scale according to the heat that is available, but it's just going to be bigger steps. So up to 1.8 megawatt per machine, of course, always depending on the conditions. And then you can just put multiple of those machines at one site. The interesting thing here is that we developed this especially for geothermal applications. So in this case, we can go into the machine directly with the geothermal brine. And how we do that is just that we have a specialized evaporator for every application. So the rest is still completely standardized and the same. The only thing that's going to be customized is going to be the evaporator to make it possible to go into the machine with the geothermal brine directly, just to take advantage of the temperature as much as possible to get higher efficiencies. And of course, this can be done with regular geothermal wells with a brine directly, or of course, we can also be connected to closed loop systems and go in with the hot water into those machines. So thank you very much for listening today. If you have any questions, I'm very, very happy to answer. Also, if anything comes to mind later on, there's all of my contact information, so please just feel free to contact me. Also, if you have any particular cases you want to discuss, you want to take a look at, just feel free to give me a call or write me an email, and I'm happy to talk about that.
Okay, thank you, Veronica. Is my audio okay?
Yes.
Okay. Okay then. So we already have a lot of questions actually. Okay,
great.
so let's go over some of the like quick questions that maybe you might be able to answer. So there are a lot of questions about figures.
Okay.
So efficiency range, heat to power efficiency, footprint per megawatt, LCOE per megawatt, and the working fluid that you're using. I mean, if there are some of these that you can't answer yet, then I think it's also fine.
Yeah. Okay. Answer to all of those questions, very unsatisfying answer. It's gonna depend. Because I mean, there is a lot of difference in temperatures. It's here in Germany, we have some regions where we only have, here in Munich where I live, I think we have around 100 degrees in the geothermal wells. There's other regions in Germany where we can reach up to 180 degrees. I know there's other regions in the world where you even get steam. So the temperature ranges, and that's the most important thing, because efficiency is always defined by the temperature difference between the ambient temperature, because we cool against ambient temperature, and the temperature difference to the geothermal heat. So it's going to depend. What I can say, in our machines, the range is going to be for the really, really lowest applications, very low temperatures. We have about 5% efficiency. The highest our machines now, our new bigger machines are designed for, is about 20% efficiency. So that's going to be the range, and where you're going to fall is going to depend on the temperatures of your geothermal heat source and also the ambient temperatures, of course. Then the footprint. So that's I can't tell you the footprint per megawatt. I don't have that. Can't tell you from top of my head, but I can tell you the footprint of our machines. So the smaller machines, they're a standard 40-foot shipping container. So they're I think 2 meters 40 by 12 meters, something like that. And they can produce up to 200 kilowatts. And then you can just put multiple machines. If you want more electricity, you have to keep a little bit of space between them. But that's also a nice thing about the modular systems. We always say we can play Tetris. So if you have very limited space, you don't have to put them nice and neatly next to each other. Of course, that's great. But if you don't have the space, we can just arrange them however they're going to fit. So I can actually say that so far footprint hasn't been a problem. We always found a way to fit the machines. With the bigger modules, so there where we can produce up to 1.8 megawatts per machine, the footprint is gonna be about, I think, 20 times 12 meters, something like this. So it's going to be a little bit bigger, but there I also have to say it's going to depend a little bit, because here we have a bit more freedom in the design. Like I just mentioned, we have a customized evaporator, but also we can customize the condenser a little bit. So for higher temperature climates, we would maybe add a little bit more area on the condenser to counteract the higher ambient temperatures. So then maybe footprint is a little bit bigger, but also your electricity production is going to be a little bit bigger.
Okay then. So yeah. So quick question is that it depends. Oh, sorry. There was one more question here. Are you able to specify what working fluid you're using for the Warza units?
Yeah. Also going to depend. I'm sorry. Because that really depends on the temperature levels that we have. So we have in the newer, bigger machines for the higher temperature levels, we have natural refrigerants. But yeah, it's going to depend on the temperature levels.
Okay then. One specific question here about the Frutura case study. What temperature goes into the ORC unit, and does it cascade to the greenhouse, or is it the other way around?
So it's in the heat is always used first by the greenhouse, and we only get the heat that is left over, that is then unused. But it's in parallel connection. So for just I'm sorry, I don't know all the case studies by heart. So if I just go back to the slide very quickly. Yeah. Okay. Yeah, so if we have geothermal brine of 125 degrees, we usually have a temperature difference then in the heat exchangers of 2 degrees, something like this. So you actually don't need a very high temperature difference. So we try to go in with the highest temperature possible. So here it should be in the range of something 23 degrees, 123 degrees going into our machines.
Okay, some more, I would say, more practical questions. What are the parameters that you need from the customer? Say temperature, pressure, fluid chemistry that you need before you can start designing an ORC unit.
I would say for a very rough first estimation is the flow rate, the temperatures, and the location so that we know the ambient temperature. Those are the most important factors. Then we can already give a rough estimation. Of course, if you already know something about the chemistry of the geothermal brine, that's very helpful to make the calculations a bit more accurate. But we can also, usually you can make some assumptions based on the region for that.
Okay then. Talking about speed of deployment, of course, like transportation time would vary, but say if there was a customer in mainland Europe, how long would it take from order to commercial operations?
So currently we have delivery time of 30 weeks, I think, for the small machines. And then once it's delivered, let's give it 2 to 3 weeks for actually connecting to the geothermal source, and you can start electricity production. So it can be very quickly.
Okay. Are there scenarios where your ORC unit has been connected to the grid, or are they mostly off-grid
Yes.
applications?
So for most of our industrial applications, it's always that the customers use the electricity themselves. But for the geothermal plant in, maybe if I can, yeah, here the one in Kirchweidach, it has been connected to the grid. So we are compliant to all European grid standards. Also, we have units that are compliant for the US. And with that, usually we can handle all other local requirements.
Okay, then we have some questions specifically from, from specific regions of the world. So someone from Azores is asking, is it a consideration? Is it a consideration for you when the fluid flow has a specific steam fraction or NCG composition? Is this something that comes into the design of the ORC?
That is actually something I can't really answer. I'm not that deep into the design. I'm mostly in the real applications because, like I said, we always have the same machines, so the design had to be done once. And I'm more into the actual applications, how to get the heat to the ORC unit. So sorry, if you sent me that question, I'm sure I can get one of our development engineers to answer that.
Okay, no problem. I mean, we can always get in touch with them, or they can get in touch with you.
Yeah.
Okay, some more questions here about other operational issues. Like, do you also consider possibilities of scaling on the heat exchanger when dealing with geothermal fluids?
Yeah. So of course, that is the one of the reasons why for the smaller units we always have the heat exchanger in between. So here we have a simple plate heat exchanger, for example, because in this region geothermal fluid is relatively easy to handle. And then into our machines we just go with the clean water. So there is absolutely no problem with scaling, and here these plate heat exchangers can be cleaned fairly easily. Something we're doing for the bigger units, for the EP1000s, is here we're mostly gonna use tube and shell heat exchangers, and of course, like in any geothermal power plant, depending a little bit on the composition, they're also going to have to be cleaned then for, yeah.
Okay, then maybe related to that, do the ORC modules come with what are the monitoring tools that come with it, and what are the like, sort of predictive maintenance
Yeah.
tools that come with the modules?
So the machines itself, we of course provide all the data points so you can monitor everything that happens inside, all the pressures, temperatures, all of the operating parameters. We also monitor the heat going in and out, so you can see all of that. But the machines themselves operate completely autonomously. So you don't have to do anything about that. You don't have to control anything. It does it by itself. You actually can't even do anything. That's something. So our basically the only signal the customers have to give the machines is the okay to operate. And then the machine can start operation. But we have remote access to the machine. So if there is a problem, we can always directly see what's happening there, and we monitor all of the machines. So if, for example, we see that the performance is dropping in the machines, we can see why that is. For example, the coolers might be dirty and they might to be cleaned. So something like that we can monitor, and then we can act quickly and in advance.
Okay then. A few more questions here. What is the minimum temperature for your ORC units, and is there a maximum temperature?
So for these machines, the minimum temperature is 80 degrees Celsius. Then we can start electricity operation. There is basically no maximum temperature. So we have a maximum temperature that really goes into the machines. For these ones, it's 150 degrees. But I mean, if the temperatures are higher, that's never a problem, because we can, one way is because we have here this intermediate, no upper limit, basically.
Okay then, there is no upper limit, and of course, in geothermal, you're not really worried about upper limits. Okay, one thing I found quite interesting is that you have this whole buyback and leasing business case.
Yeah.
So how does this work out for, say, an emerging or kind of a startup geothermal company, or a more emerging region? What has how does this also work for you internally? Like how is this something that is also feasible for the company or sustainable for the company?
Yeah, so we have different partners that we can offer such finance solutions with, because, like you already mentioned, in different regions of the world, it's going to be different. For example, one company we work together is E.ON. With them, we also did the project here in Germany. We're currently also with them doing a project in the cement industry, which is with our bigger EP1000 module, and which is also a leasing option. So we have been doing this with them quite a bit, but they are only in some regions of the world. And then we have other banks that can offer leasing solutions or even PPAs in other regions of the world. And for some, I would say the more difficult regions where not a lot of banks want to do solutions like that, we have found that export credits are a great opportunity to also finance solutions here. And then something we can do, so this is going to depend a little bit for regions, let's say Europe, North America. It's very easy to have flexible buyback options directly in the contract, and we can be very flexible with that. Usually it makes sense to have a minimum operation time, that you don't give back the machines after 1 month of operation, but that we say, okay, the machines have to operate at least for 2 years, something like that. And then we can buy them back for initially agreed sum. So there's a lot of flexibility in that. Or also, we can start with the leasing option, and then if you say, okay, I want to make the investment myself, that is also a possibility.
Okay then, so there's seemingly plenty of interest from, say, more starting regions when it comes to geothermal. Say if there is a company that wants to go into, say, wellhead generation using ORC units, do you also give some sort of technical advice on what are the other surface infrastructure that they need to have to accommodate your ORC units? Like, do they need evaporators? Do they need scrubbers for their fluids?
Yes. So what's really important is that we have this external heat exchanger, and then depending on the geothermal fluid, of course, that's going to have to be cleaned. And what's really important for our machines, so we can't do island electricity production. We always need a stable electricity grid that we can connect to. So that can be either just the normal electricity grid, or if you have maybe generators that are big enough operating there anyways, or we're already creating a stable grid, we can also connect to that. But we can't produce an electricity grid ourselves, so that is really important.
But then that works out well if say they have a large scale industrial user for electricity, right?
Yeah.
Okay, then are there any specific, say, chemical parameters that are needed for your heat exchanger? Are there like pH or acidity, other acidity issues that companies need to be, I mean, clients need to consider?
So for our internal heat exchangers, we have pretty strict regulations for pH levels and everything, but that is why we have this closed loop in between. And this is something where we also give the exact parameters in the beginning, that once it's filled with the clean desalted water, I hope that's the right English word, then it's the loop is closed. And you have a pH control also in there to keep the pH levels right for this closed loop system, that the heat exchanger is not damaged. But it's a one-time filling, and then it's all good. So we don't have any, I think that's important to mention, we don't have any water consumption in our system. Generally, we don't have any consumers. So it's completely closed loop, everything.
Okay, so we have maybe time for two more questions. For the units that are water cooled, are there any specific requirements for the cooling water? I mean, temperature, chemistry, flow rates, or is any kind of ambient conditions okay with your units?
So for the water-cooled units, yes, we have restrictions. To be honest, so this is something we are only doing this one project right now with the water-cooled systems, because we're not seeing very high demand with that, because usually you just don't have the cooling water available. So we're not really promoting the system anymore, and instead focusing on the air-cooled systems. If there was really high demand, we can offer those solutions, but from all that I've seen, usually cooling water is very rare. So it's better just to go with the air-cooled
Yeah,
options.
yeah, I think there are like two water-cooled geothermal power units
Yeah.
that still exist, like the whole world. So I don't
Yeah.
think it's a growing market.
So it's something we actually have the technology from our marine applications, because there, I mean, you're basically driving on your cooling source. So there we can just use the seawater as cooling fluid. So that's why we have this technology available to do it with the water cooling. But of course, it has to be adjusted a little bit for the land-based applications. And there's simply not really the applications. Unfortunately, for thermodynamics, cooling water is of course always great, because you don't need the power for the air coolers, but it's simply mostly not available.
Yeah, I agree. Okay then. Based on, I mean, I understand that most of your client base is on the industrial heat sector. So, what do you think is the strength that kind of this experience has given Orcan Energy, and like, what is the experience you got from this kind of from your experience in the industrial heat sector that you think can be transferred directly to your geothermal clients?
Yeah, so I mean, we have a lot of heat in just a lot of experience in just operating the machines. So that is a big advantage. And also, it's this flexibility that is for the industrial sector, it's a must. because heat sources have very big fluctuations and are very unstable. So the machines always had to be very good to handle part load, to handle quick fluctuations. And now that can really help us in the geothermal sector to handle these fluctuations from the demand side. So the heat source is stable, but if you have other heat sources, heat users, the demand is gonna fluctuate. So it's really great to have this um, to have this extra thing to combine it with, that together we can create we can make the most out of the heat that is available.
Okay, kind of related to that, there is a series of questions here about modulating power generation. So, from your experience, are there any issues related to, say, having to turn on and off the units like regularly, having a long standby time? Do you think there are any operational issues that can happen?
That's actually the great thing about ORCs, is that they don't have any issues compared to steam turbines. I know that they can be very damaged when they have unstable operation if they get turned on and off too much. And ORCs actually don't have that problem, especially with our turbine technology. So in the smaller units, we have screw type expanders. They are very, very robust. And even in the bigger machines, now we use turbines, but it's still a very robust single stage turbine. So they have no problems at all turning on and turning off a lot, and also handling those part loads. And also very quickly, they don't get damaged because the now I don't have the um, thermodynamic curves with me, but you never go into the sorry, it's a little bit hard. I never talk about these very technical issues in English, where the part of the curve where the droplets get built that can damage the blades on a steam turbine. In the ORC, the curve is a lot different, so you're always only in the dry part basically, and you don't get droplet formation that can damage the blades.
Yes, yes, I agree. And also, that's in a steam turbine, starting up from completely shut down conditions can take some time. It's
Yeah.
this. I imagine it's less of a problem for an ORC turbine, right?
Yeah. So our machines go from startup to full load electricity production in about 2 minutes. So it's pretty, that's something we had to do
Almost.
for the industrial
Yeah.
processes. Yeah.
Yeah. I mean, that's almost nothing, basically. Okay, then. So there is plenty of interest from in our audience from, say, people from South America and Africa. So can you tell us a little bit about? I mean, as a last question, can you tell us about the expansion plans for Orient Energy? Like, are there priority regions for your geothermal business?
Yes. So generally, our main focus right now is on Europe, North America, and Asia. But especially for geothermal, we of course see that there are lots of other regions with a lot of potential. So we're always open to other regions and to expand all over. But these are just the regions where we see the most potential right now.
Okay, then. So maybe you can flash your like contact details here while we wrap up the webinar, just so everyone from the audience can get in touch if they want to. Yeah, but I mean, my personal advice for a lot of emerging regions is that they should start small. I mean, there's no sense in trying to scale up instantly to, say, 20 to 30 megawatts when you have an unproven resource. And so I think that modular solutions are really a really good way to get into that market, and also like they are excellent proof of concept projects if, say, if you need more investors, if you need more policy support. So I think these kinds of solutions can be a great way to scale up geothermal industries in starting areas. Okay, then I think that's all the time we have. Thank you, Veronica, for that presentation, and
Thank you so
we
much,
hope to
Carlo.
hear more from Orcan in the coming years. To everyone in the audience, thank you for coming. Thank you for the questions. We will publish the recording of this webinar soon. And also, if anyone has more questions to ask Veronica, just get in touch with her, or maybe we can also get in touch with you. We'll see. Um, Thank you, everyone. Thank you, Veronica. Have a happy weekend.
Thank you so much.
Bye.